Hello, this is Math Chess from Almost Cool. I am doing a calculus live stream on this uh, very cold Monday night, actually. It's snowing quite a bit today. But, um, nevertheless, we have some math problems to do. So, my students seem to be having no trouble at the beginning of this semester with problems they've been asked to do. So I got I received no math problems from them to solve for them in this live stream, but they will be talking about volumes of rotation this week and integration by parts. So, or sorry, yeah, integration by parts. So I have two problems, one from each of those topics that we will do in this live stream. If you have problems you'd like me to solve, send them to me either in chat or in the email that will be listed at the bottom left of the screen. Here is problem number 1. What is the volume of the solid obtained by rotating the region bounded by y equals x squared minus 4 and y equals x minus 2 about the line y equals 1? So y equals 1 is our axis of rotation, and then the parabola and the other line are the bounds of the region being rotated. Now, the first thing we're going to want to do, this is up to you. You either want to graph the region or you want to find the intersections of the region. I'm going to do the intersections first, and then I'm going to graph the region. So, first we set the two equations for our two curves equal to each other, and we solve for x. So, we notice that we're going to have a parabola, so we move all of our letters and numbers to one side of the equation, leaving a 0 on the other side. We get this nice parabola, which we're going to factor. And now we know that at x equals 2 and x equals -1, we're going to have points of intersection between our two curves. So now we know the endpoints for our integral. Well, if we're going to integrate with respect to dx using the disk method. But if we were going to integrate with respect to y, we'd need y endpoints, but we at least have the x coordinates of the points of intersection, and from those we could find the y coordinates if we needed them. We're not going to do that. We're just going to use the washer method. So here we go. We find that the curves intersect at -1 and 2, which I said. We look at the graph of the region. This part of the graph is the region that's being rotated. This green line represents the axis of rotation. So I'm going to draw a representative rectangle that's going to represent the washer that, the rectangle that will be rotated to form the washer that we will model you'll use to set up our washer method. So here we go. This is a representative rectangle. It goes from one of the curves to the other curve. Notice that we do not have to change. We can use these vertical rectangles the whole way from one point of intersection to the other on our integral. We don't have to. Sometimes these regions have interesting geometries where you have to split up the region into different pieces, each of which can be done by some sort of integral. This one was nice. We could use the same. We can use one integral to do the entire solid of revolution. So from here, what we have to realize is that this black rectangle is not what we're actually going to integrate. Normally, when we find a representative rectangle, we're going to let dx be the small side of this rectangle. We're going to find an equation that describes the tall side of the rectangle, and we integrate that. But since we're using the washer method, what we actually have to do is find this rectangle and set up an integral for it. This red rectangle represents the region that's obtained between the parabola and the axis of rotation being rotated around that axis. And it'll represent a much larger solid than what we're actually looking for. But we first find that volume, and then we find the volume obtained by rotating this orange line around the green line. And if we subtract this region, which is going to be done using these blue rectangles, from the region that we looked at already with the red rectangles, if we subtract the blue region integral from the red region integral, we'll get the integral we wanted, which is this this black region here. So this is how that will look. We first find the height of the red rectangle to be the difference between the axis of rotation and the blue parabola. And we simplify a little bit just to make the integral come out nicer at the end. And the height of the blue rectangle is the distance between our orange line and the axis of rotation. And again, we simplify a little bit of the algebra so that we can have a nicer integral to take later on. Now that we know the height of this blue rectangle and the height of this red rectangle, we plug those into our washer equation, and we get this integral. The integral from -1 to 2, those are our points of intersection, of the difference of squares between the height of our blue rectangles and our red rectangles. So that'll give us the volume that we get when we rotate the parabola around the axis of rotation. It'll also give us the area of the line being rotated around the axis of rotation, and then by subtracting one from the other, we get the bounded region that we were looking for in the first place. So we do some algebra to simplify the integrand, and we get this integral here where we can use the power rule on every chunk inside of the integrand. And from here, I leave the exercise to you, the viewer, to do on your own using the power rule. Oh, there's a typo. We have to multiply the whole thing by pi from the integral of rotation formula that we learned. So just multiply every one of these integrals by pi, and you'll get the correct volume. Other than that, this is the integral that we're looking for. Okay, so that was a volume of rotation. Here is an integration by parts question. So we want to find the antiderivative of x squared cosine x with respect to x. So to do that, we first have to divide up our integrand into a u piece and a dv piece. Now, our dv piece is one that we're going to have to find an antiderivative of. So we want to figure out what's easier. I mean, we can see that there are only two pieces here. There's x squared and there's cosine x. We have to look and we have to decide which of these pieces is easier to take an antiderivative of. Now, they're pretty easy, both of them, but if we integrate x squared dx, we're going to get 1/3 x cubed, and that goes from a polynomial of lower degree to a polynomial of higher degree. It actually increases the complexity of the problem. So we want to pick the other one. If we pick cosine and we integrate it, we started with a trig function. We end with sine, which is still a trig function. There's no extra complexity. And by choosing x squared to be our u, when we take a derivative, we go from a quadratic expression to a linear expression. And so let's do that. We let u equal x squared and dv equal cosine x dx. And the reason being, as we said before, x squared is easy to take derivatives of, and cosine is easy to find antiderivatives for. So we find those. We get du equals 2x dx and v equals sine of x. And then we plug this into our integration by parts formula, which is going to be the integral that we start with is equal to u times v, so x squared sine x, minus the integral of v du. That's where we get sine x times 2x dx. I'm going to rewrite this as 2 times the integral x sine x dx. This is purely cosmetic. but I prefer having my polynomials come before my trig functions when I'm multiplying. So that was purely because I think it looks better this way. From here, we notice that x sine x dx is another integral that we want to do using integration by parts. So we have to pick a u and a dv. If we pick u to be sine x and v to be x dx, then it undoes exactly what we just did. So we go the other way. We let u be the polynomial x, and we let dv equal sine x dx. Doing that and plugging into our formula, we get the -2 times the integral from line 2 becomes -2 times negative x cosine of x minus the integral of negative cosine x dx. We remember that x squared sine x carries down from the second line to the fourth line, or second line to the third, second equation to the third equation. There we go. From here, we multiply everything out, and we take the antiderivative of negative cosine of x, and we end up with x squared sine x plus 2x cosine x minus 2 sine x plus c. And I'll leave as a problem for you guys to do, to take the derivative of this antiderivative to see that we did it right. If you find any errors, then comment below, and I will fix the video. Since there are no other problems presented to me this week for this live stream, we will end it there. Thank you for watching. Hope you have a great day. Hope you have a great week learning calculus, and see you next Monday. Bye.